So in this video I want to talk about some of the pitfalls that people can end up in when undertaking a linear regression, and also why it is important to consider the structure of the data. And by structure I mean the underlying causal structure that led to the generation of that data in the first place. So the problem setup might be as follows. We may have a predictor x, and we're primarily interested in its relationship with some outcome y. But at the same time, we may have access to a number of other variables, which sometimes are called control variables. These may include things like demographics, like age and gender, social economic status, and so on. Now, in a very simple scenario, we may just have access to x and y. And in which case we might describe the model that links x to y as follows. In a linear model, we have y, which is a function of x, which is beta times x plus some residual noise, epsilon. And if we undertake a linear regression, we estimate that coefficient beta. And in this case, for this example, we get a coefficient estimate of -2. And this looks correct. And many people would like to interpret this by saying, well, for instance, an unit increase in x leads to a corresponding decrease of 2 units in y. Now, as I said before, we may have access to lots of other variables that we may use as control variables. And control variables are generally used to explain some of the variance in y that is actually not attributable to x in the first place. So the idea is that we should consider these variables as they may be influential in explaining why our y variable is as it is. And in this case, if we include all of our variables, including x, and all these controls, we end up getting coefficient estimates for the relationships between each of these variables and y. And if these are normalized, these are correlations, and as such, each of them will sort of partition the resulting variance in y and explain as much of it as the model can do in order to minimize the error in the model. Now, the question is this a good thing to do? So is including these control variables, in this case a very naive way, a good thing to do? And does it affect our estimation of our coefficient of x onto y? And I think many people would intuitively say, well, of course it does. You've just said, Matt, that if we're including all of these variables, then they will each sort of share the variance in y according to their sort of respective importances. But what I'm also going to argue is that that is not the only issue. The other issue is that sometimes the inclusion of these variables leads to very spurious estimation of the main relationships that we're interested in. Now, traditionally, there are 3 methods that people use in terms of deciding which control variables to include in their model. So when I was at university almost 10 years ago, there were 3 methods that were primarily used: the sort of all-at-once method, chuck all the variables into the model, the forward method, and the backward method. And when doing this, we were told that we should keep in mind that we should seek the most parsimonious model. And this isn't a philosophy that is shared by everyone, but it is very commonly used in research still today. So parsimony simply means we should try and achieve the simplest model we can, which means only including enough variables that are necessary to explain our data. So the all-at-once method, as I said, is just including all the variables that you have access to. That's not going to lead to a very parsimonious model. The forward method is you start with only one variable and then you gradually include more variables until some criterion is reached or fulfilled. That criterion may be something like, are the new variables significant, or is the fit on your model still increasing in a significant way? And the backward method is sort of the inverse to that, such that we start off with all the variables and then we gradually remove them according to some similar criteria. So the question is should we be interpreting the models derived using these methods? As I mentioned on the previous slide, we might get a coefficient estimate out and be tempted to say, well, what this coefficient means is that for 1 unit increase in x, we get a corresponding increase in y by some beta quantity. And what I'm going to argue that we shouldn't be interpreting models that are derived using these methods, and these methods are very commonly used, as I mentioned, in research today. So in order to demonstrate these problems, I'm going to take an example from this book called Elements of Causal Inference, which I highly recommend, by Peters, Jansing, and Scholkopf. And the reason why I want to use this example is even though it's taken from the point of view of structural causal modeling or structural equation modeling, we can use that to generate data and then demonstrate quite succinctly how our choice of control variables affects the resulting coefficient estimates in our linear regression. And this is very important because linear regression is a ubiquitous tool that is used in many different fields, and many people argue that because it's a simple technique, that actually we end up with a model that is interpretable. But I'm going to argue that actually, unless we consider our structure and we get that structure correct, that we can end up with models that are far from what they should be and mislead us quite severely. And so the result is that we should consider as much as possible the underlying generative structure. So the example I'm going to take from that book is this one here. So this is a structural diagram, or sometimes sort of a form of a probabilistic graphical model, and it allows us to illustrate the relationships, the causal relationships between variables. Now, let's pretend we don't know this structure, even though I've given it to you here. In reality, we won't have access to this, but in order to demonstrate the pitfalls associated with undertaking a linear regression, I wanted to include this as a means to compare our linear regression estimates against the ground truth. So having this model will enable us to say, well, look, if the data is truly generated according to this structure, can we recover that structure using linear regression? And if not, why not? So the equations on the right are structural equations, and they simply describe the relationship between these variables. This choice of graph is completely arbitrary, and you could choose any different graph that you wish. But just to give you an example, C has no arrows pointing into it, so it's solely determined by its own random noise. It could be random normal distribution. A, again, is its own sort of noise source, so 0.8 times some random normal distribution. K is a function of A and its own noise, X is a function of C and A and its own noise, and so on for the rest of the variables. So one of the advantages of having this causal model in front of us, which again we may never have access to in real life, but we're going to use today in order to demonstrate why a naive linear regression approach will lead uninterpretable results. But one of the advantages is that we can actually calculate very simply the resulting influences between these variables. For instance, in the linear Gaussian sense, we can simply calculate the relationship between x and y by multiplying the path coefficients together. So the actual influence of x to y in this structural equation is -2 times -1, which is equal to 2. So that is the effect of x on y through this path. Now, as you can see, there is also another path here, and if we want to sum the total effect on x on y through both this sort of mediated path and also this indirect path, then we would have to sum the resulting path. So this would be -2 times 1 times 2 plus -2 times -1. But we're going to use this because if we're going to be using our linear regression to estimate the relationships between these variables, we can then compare those estimates against what the actual relationship is based on the underlying generative structure. So in order to do that, again, I'm going to take this example from that book I mentioned, and I'm going to code it up in Python. They used R in theirs, but I'm slightly more comfortable with Python. And I'm going to use the stats models API to undertake ordinary least squares regression. So these equations here should represent the same equations that you saw here. Feel free to check. And I'm going to use a sample size of n of 2000. So you can choose whatever number you want. Obviously, for lower numbers you get less accurate results, but I want to give the linear regression a good chance of doing its best. So the first thing to notice is, again, that there is this two paths that link x to y. One is through D, and the other is through A and K here. So I've drawn in red this path here, and if we're primarily interested in this mediated path from x to y, then we'd have to somehow adjust for this indirect path. And if we don't adjust for that, then our estimation of x and y is heavily dependent on which variables we include in our model. So I'm going to demonstrate just including some of these variables and regressing them to see how close we get to the sort of target or the ground truth coefficients here. So if I regress x and d, I actually get the correct result of -2 here. So that's great. So far, so good. Our regression of including these two gives us the correct results. What if we now regress d and y? We're looking for a coefficient of -1. For some reason, we actually get -0.65, which is not correct. As we'll come to see later, actually there's an indirect path here from d to y, which sort of follows this flow of information here. And I'll come on to the rules about why that flow of information exists soon. And then what if we're primarily interested in this effect of x and y, and we might include d. Again, we don't know that this is the actual structure of the data, but we might include d as some available control variable, in which case we get a completely incorrect result for x, which should be 2, but in this case we've actually got -0.85, which is not only wrong, but it's also an inverse relationship. We're looking for a positive coefficient. We've actually got a negative coefficient. And as we'll come to see, that's because of this indirect path that exists here. Controlling or adjusting for d, we've actually got the correct result for d now, which is strange because in the previous demonstration we actually got an incorrect result for d. So now we've got the correct result for d, and we'll see that that's because we've blocked this path that links d to y indirectly. So what are these rules that I'm sort of talking about blocking a path? Well, essentially they're as follows. If we look at this example first, this describes an arrow going into a variable going to another variable here, and if we include this variable in our regression model, we effectively block the path of the flow of information between x and y through d. Another example, if we have sort of a situation that looks like this, where arrows are going out of a variable that's included in the model, then we will block the path between the two neighbouring variables, so x and k will no longer be able to communicate through a. And finally, this variable is black because it's not included in the model, and this actually blocks the path. So here an example is c going to x, and a going to x. This is a collider, in which case the flow of information is already blocked due to the structure of these arrows. If we were to include this variable in the model, we'd actually create a flow of information between these two, and that's called explaining away. So with these sort of rules in mind, we're able to actually choose the variables we include in our linear regression intelligently. But again, in reality, we don't have access to this model, so the variables that we choose are actually very difficult. It's very difficult to decide which ones to include. But if we do account for these, then we'll see, well, if we are interested in this relationship with x and y, then we need to adjust for this backdoor path through a and k. And that means choosing variables that allow us to block the flow of information through this path. So this is called choosing variables from an adjustment set. And these variables in the adjustment set include a. If we include this variable, we block the flow of information from x through a to k and to y. Or we could include k for the same reasons. X is no longer able to communicate with y through this path. Or we can include both a and k. And we also notice that including f, g, and h shouldn't have any influence on our estimation of x onto y. So again, if we have access to these variables as control variables, and we don't know which ones to include, some will have dramatic effects on our estimation. For instance, as we saw, if we included d, we completely distorted the effect of x onto y. If we include f, however, f has no influence between x and y, and so shouldn't affect our estimation of x onto y. But then that assumes that we're already adjusting for this backdoor path here through a and k. But with this in mind, let's see if we can actually get the correct coefficient estimates that we want. So let's include a now. So we're looking at the relationship between x and y, and we're, in quotes, adjusting for this a variable, which is part of the adjustment set. In which case we actually get not only a correct estimation for the relationship between x and y, which is now 2, which was this minus 2 times minus 1 equals 2, but we also get the correct estimate for a, which is 1 times 2 here on y. So we get the correct estimates for both in that case. Let's try k instead. Again, we get the correct results. X is still 2, which is ideal, and k is also 2, which is ideal. What happens if we include more than one of the adjustment set variables? Well, this now shouldn't affect our estimation of the x coefficient, and it doesn't. This is still 2, which is great. But it does affect our estimation of the relationship between a and y, which is now near 0. And the reason is because if we've included x and k in our model, there's literally no way for a to communicate with y. So this relationship is reduced to close to 0, whilst our relationship between k and y is still correct at 2. If we include f, we can see that this has no effect on our outcome y, which is close to 0, which is great. But because we haven't included any variables from the adjustment set, now our estimation of x is wrong. If we include c and a, then our estimation for x is still correct because a is part of the adjustment set. C is not correct because we've actually blocked the path between c and y by adjusting for both x and a. So the takeaway for this is that the estimation for the coefficients varies wildly depending on which variables you include in your model. These are called adjustment variables, part of the adjustment set, and they're used to sort of block indirect paths or backdoor paths that link the variable of interest to your outcome variable. And it's so dramatic that it can even invert the correlation sign. So clearly we've been able to use this synthetic data where we know the underlying causal structure in order to assess whether or not our linear regression can recover the true coefficients. And what we've seen is that actually it can only recover the true coefficients if we have a strong consideration for the underlying causal structure. And this may never be available to us. So if it's not available to us and we haven't got sufficient prior knowledge with which to inform our choice of control variables, or in this structural causal sense, the adjustment variables, then we should refrain from interpreting our models. Instead of saying, oh, this coefficient means for 1 unit increase in x, we get a such and such increase in y, we should instead say, well, we have no reliable way to know whether or not our coefficients are correct. Therefore, we shouldn't interpret them. They may still form predictive models in that the models themselves may be useful for achieving some low error on a prediction task, but that we have no way to infer the true relationships underlying the data. So this should highlight the fact that we have to really consider the underlying structure of our models carefully. And in some scenarios, this may be very difficult. In other scenarios, it may actually be intuitive and simple, particularly if you have access to randomized control trial data and your experiments are heavily controlled. I hope that's been helpful, and I hope that's illustrated some of the issues associated with a naive approach to linear regression. And by naive, I include the methods that seek parsimony, including the forward and backward method.